So the first thing I want to do today is go over section 2 on the homework. So the important outcome for everybody here is I'm pushing homework 2 back a day. Homework 2, whatever homework we're on, because of question 2. I want to go over how to do it, and then I want to give you more than just 12 hours to do it. So I'm pushing it back a day. I will be assigning the next homework today. I'm gonna go write it out and get it going because it also needs to be due next Wednesday. So I am pushing this back a day, but I'm not pushing the next assignment back. Just because again, I need to give the TA a day to grade it. Or I can ask questions on it, about it for the exam a week. So still trying to be as fair as possible. Well, making sure that you do question 2 correctly. So the first thing that I noticed when I went back to look at this is that I fat fingered the expression. So the expression should be k squared plus a over 2 in order to have the outcome and the math that I had done in advance. So, oops, this should be. 2. It will mostly work with 2, but this is supposed to be k squared plus k over 2. Oh yeah, resubmit. Oh, I was gonna say that's okay. Just leave it. I don't know what the result is supposed to be with k squared plus 2 over over 2. I did the work with k squared plus k over 2, and it's probably fine. I don't know. What did you find with k squared plus 2? What was the same? It was basically the same. Yeah, the reasoning for the k is basically that it adds. Well, so I'm gonna go through the process of what this expression is supposed to be doing. And I don't know if that was perfectly clear what that was supposed to be. So we have some array, and let's say that when we hash the array, we end up in index 1. That's where that's the home slot for 1. If we're doing linear probing, then if there's already something in index 1, we're going to look at index 2. If there's already something in index 2, we're going to look at index 3. And we're going to do that over and over until we find an empty slot to put it in. With quadratic probing, this k is the number of times that we have looked. I don't know if that was clear, but we start by looking once. We're going to set k equal to 1. So the first expression is 1 squared plus 1 over 2, which gives you a total of 1. So this tells you the offset from the original place that you're supposed to look. So 1 plus 1 is index 2. If there's something already there, then instead of just looking at the next thing, you're going to substitute k equals 2. So you end up with 2 squared plus 2 over 2, which gives you 3. 4 plus 2 is 6 over 2 is 3. So you're going to take the original spot 1 and you're going to add 3 to it, which tells you the next place to look after index 2 is index 4. Then if that has something in it, you're going to look at index 3 squared plus 3 over 2. And that is 9 plus 3, 12 over 2, 6. 1 plus 6 is index 7. And you're going to take any of these, mod the table size. So if we end up falling off the table, then we'll loop back around. But the idea is that we're not searching sequentially, we're searching with a quadratic pattern. This is 2 squared minus, or sorry, 2 to the first, 2 to the first minus 1, 2 squared minus 1, 2 to the third minus 2. It's based on a quadratic. Basically, a plus 2, plus 3, plus 4, plus 5. That ends up being a quadratic nature expression. So I'm going to make an announcement for those who aren't here, aren't zooming in, don't take a look at the recording before that, so that people who aren't here know that as well. But does anyone have any questions about that? I apologize for 1, the typo in that, and 2, for I don't think I explained that well enough. What I was looking for there, so hopefully this clears that up. Yeah. K again? K is the number of times that you have come into a collision. If you find a collision for the first time, you'll use this. If you've already had 1 collision, then you're going to use this. If you've already had 2 collisions, you're going to use this. So this is the number of collisions that you have seen so far. And this is what you add to the original home index. Not to the last place that you looked. It's added to the home index. So index 1 was the home index, 1 plus 1, so you're gonna look at index 2, then index 4, then index 7. And if the table were size 6,
You do start it from the initial index that was going to maps, right? So.
yeah,
Is that the home index, is that what you're saying?
yeah,
So home index plus this quadratic split.
yes, yeah.
What do you think?
I changed it to tomorrow midnight. If that does not work for your schedule, for some reason you're really, really busy for the next couple of days, send me an email and I can make an exception. This is my time. I will work with you to make sure you can turn this in, do your best on it, and you have time for the next one ahead of the exam next Friday.
Is the tree slab pretty long?
The next one, probably I'm gonna have you implementing a binary search tree. Which, depending on, I don't think it's a ton of work. But it depends on how intuitive this is and how good you are at taking that intuition and writing code for it. So I could see it being a very easy assignment for some and a very difficult assignment for others. Will be as available as I possibly can to help out. I recommend starting early so that if you do get stuck, there's time for me to help you out and for you to make those changes
And that I will need to do next round.
next Wednesday. Because we have an exam next Friday. And I want to make sure you get feedback on that tree lab before I ask you questions about it at the exam.
When will you be posting the study guide for the exam?
Right. I try to do it a week ahead of time. So it should be Friday, it should give you the long weekend to start figuring out if you have questions, and as usual, we'll have that Thursday before the exam for a review session. So people can ask questions, we'll go over some examples, by then I'll have written the exam, so I can answer questions about the exam. Other questions?
So is it just a tree lab and then is that the last one or are we gonna have
We're
one?
probably gonna have one more assignment after that we'll do with either something to do with heaps, something to do with graphs, something. So the reasoning is a lot of this content is actually going to be recovered in a bit more detail in algorithms, so I'm not hugely concerned about making an exam for it. We'll have that exam in algorithms, which is why there's no final in the class. I figured I'd be covering everything that is supposed to be this class by the end of week 9. So I could write an exam for that.
Is there any way to get it small then? Because I got a lot.
Yeah, yeah, I'll try to make it something that is fairly contained. But I want to give people a little bit bigger sample size for grades as well, because I know I haven't really assigned. There have been a ton of assignments, so if you missed an assignment or did really poorly on an assignment, I want to give you the opportunity, but that's not affect your grades much. There are no other questions. I'll make that announcement on Canvas, but I very much wanted to make sure that it is clear to people in class. Okay, the next thing I want to do is live code a heap, because I think that we very much want to see this working in practice. So can somebody summarize what is a heap? What can we do to a heap and how is that done?
Stored in the view, but it looks like a tree, you mentioned.
Yeah, it's stored in an array. It looks like a tree when we think about it.
It's got the max element at the top.
Yeah, so we have max heaps and min heaps. If it's a max heap, the root has the maximum element. If it's a min heap, the root has the minimum element.
Don't the leaves have to be all the way to the left
Yeah,
to start?
yeah, every row, except for the last one, has to be full. In that last row, everything has to be as far left as possible. Every parent is greater than its children. How do we insert into a heap? Yeah, we start kind of at the next open position, we insert there, and then we do this really strange procedure called heapify up. That involves swapping the current with its parent until the current is greater than. Or is less than its parent, I guess, would be if it's a max heap, or greater than its parent if it's a min.
So let's call a what?
We call that heapify up. You can call it bubble up, you can call it up heapify, one of those, that's usually what's used. I didn't invent it, don't shoot the messenger. How do we delete from a heap?
Root,
We delete the root by,
switch it with the last.
yeah, we swap it with the last element in the heap, so the lowest level, farthest right node, swap the root with that. Then we delete the root, and then we heapify down, or down heapify, or bubble down, whatever you wanna call it. We're gonna compare the node that starts at the root with the largest of its children. And if it is smaller than that, if we're in a max heap, we're gonna swap it with the largest child, and we're gonna repeat that process until it is no longer true or it is a leaf. So that's really the difficulty of implementing a heap. The other thing we need to care about is, since we're storing this in an array, where is the parent, where is the left child, where is the right child? We'll need that to be able to do all of those heapify down, heapify up procedures. So let's go ahead and start this process. We're not in 212 anymore. So this is its own separate idea. So I'm going to make a new package for this, it's called a heap. It's a new structure inside of heap. We'll make a class called. Gonna make a max heap or a min heap. I'm actually gonna have us make a min heap, because we talked a lot about max heaps, and it turns out to not be too many changes between a min heap and a max heap. But let's make a min heap. So what we want to do is we want to make sure that we want this to be generic. So we want to make this a min heap of T, but not just a min heap of T, because there's an additional restriction that we have to have in order to be able to have a heap. What is that restriction? What do we have to be able to do to these values to be able to store them in a heap? Compare them. So we need to extend comparable. So we need to make sure we do this. I'm also going to make sure that we implement everything that we need to, because I actually want this to adhere to an interface and not an interface that we write. So I'm going to implement the priority queue, the existing priority queue interface. Tells us that we need to import that. Let's see, that is interfaces dot queue dot priority queue. That.
I just did java.util. This is my did.
Java.util.priority queue.
Okay.
So the issue with that is that's the actual implementation of the priority queue, so if we wanted to use the built-in priority queue rather than make our own, that would work. So maybe we don't do this, and we'll just implement the associated methods, which is unfortunate. It would be better if we could do this, but I actually have to look up exactly what that import should be. I must be thinking of something that has been stopped being a thing. So, all right. What are the fields that we want to keep track of in our queue? So I think that's gonna be the first index in some kind of array structure, but we definitely need the array structure. So that's going to be an array of T that we're gonna call, I guess, elements. What else? Could probably, since this is a field, make it private. What do we want to know? We might want to know the size. We might want to know, this one's probably optional, but it'll make our code just a little bit shorter. The capacity. This would tell us if we need to resize our array. Let's make a constructor. What do we want for this? Probably take a capacity. When we do this, we're going to say set the capacity to be the passed-in capacity. We want to set size to be 0 because an empty heap is empty. And then we want to say, we want to initialize our array of elements. If you're going to have a generic T array of elements rather than an array list, and I would argue that we only need a regular array, the way we're going to do this is we're going to instantiate a bunch of comparable objects and cast them into an array of T's. So basically, you say, we're going to make a new comparable array of size capacity. But we now need to cast, once this returns, we need to cast this as an array of T objects. And that will get that done. So this is the way to work with arrays and not array lists. Just wanted to showcase that because I'm not sure if people have seen it before. Whenever we have something that is comparable is an object, so we can instantiate one. This warning is just telling us if these can't be cast into a T array, you're gonna have problems. So I think that's our constructor. That will initialize the object for us. Let's start with some easy methods. We want a publicly accessible size. What should size do? How should we get that size? Return size. We already have a field for it. Done. How about is empty? How can we determine if this heap is empty?
Return size equal to 0.
Now make sure it's size equals 0, because if we return size equals 0, we'd actually be setting size to 0 and then trying to return size, which is not a boolean, it's an int, and we get all sorts of fun. Java occasionally does this, where if you use a single equals, depending on whether it's legal or not, it will actually do that kind of setting. So one way that you can actually do this is you can, I'm gonna do something that makes no sense here for a second, but This is going to set size and compare it to 6. In the same thing. So this is just one way that you can do an assignment and a comparison inside of a loop. If you haven't seen this before, it's perfectly reasonable to set the value of something. And sometimes this saves you from the fence post problem of you need to set a variable to something, and then you go through a loop, and then at the end of that, you need to set it again. Before, in preparation for the next pass. You can take those 2 lines and convert it into 1 if you do the assignment inside of the while loop. That's obviously not something we want to do right now, but just something that I wanted to demonstrate is something that you can do in Java and actually in most or all C-like languages. All right, those are the easy ones. Let's start tackling something like add. So add is going to we want to add some kind of T to this. So first thing we should consider is there any way that this could throw an exception or should throw an exception?
If you've already reached capacity.
Yeah, if we've already reached the capacity, we don't want to add to something that is past the capacity. I think that's the big one. We could technically try to add null. I don't know if that may be something that we want to look for depending on that. So let's say if, are we going to get at that? We want to say if the size of this is greater than or equal to capacity. Then we want to throw what kind of exception makes sense here? Illegal state, I love that. Import that probably, let's say.
What does that do again? The throws, like when you put it in the method header?
It just tells the compiler that this method might throw this exception. So that allows you to do things like 1, throw it, and 2, put it in your documentation, if you have a way of auto putting it in your documentation. So we just need to say something like keep is equal. And that tells the user exactly what went wrong. If we don't have this exception be thrown, what do we want to do?
Is this the same inserting the?
Yeah, well, it's adding it to the end, so we're not quite inserting yet, but we're gonna be adding, and then we're also going to be separately from this doing a keepify up procedure. So this is just add with an eventual keepify up that we're gonna write separately.
We could do something like if data is less than.
We're gonna worry about the heapify up procedure separately, I think. We're gonna take those and make them separate methods. Just in case something else were to need to call heapify up, that way we decoupled it from the add procedure.
Pass in data added to where size is.
Yeah, so we want to do something like, we want to put it in our elements array, elements of size equals data. Then we need to bump up the size. Does anyone know how to take these 2 lines and turn them into 1 line? Yeah. So just like with that while, you can do an assignment and a comparison on 1 line. Here you can do an index and an operation. And where this plus plus goes tells you which one happens first. So if this plus plus goes afterwards, says take data, put it at elements of size, and then bump up size. If we instead put plus size, this is telling us to do the exact opposite. This says bump up size and then put data at elements of the new size. So in this case, we very much want this to be at the end. Because we want to store it at size and then we want to bump up size. For clarity though, I think I'm actually gonna take this and make this 2 lines. I just wanna make sure that people know that if you ever see that shorthand, that's what's happening. After this, we just need to call heapify up. And that will make sure that whatever we just added gets bubbled up and we have a legal heap at the end of it. So we have not written heapify up, so let's go make sure that we do that. All right, so heapify up actually probably shouldn't be public. I'm gonna make this private. And the reason is no outside code should be calling heapify up without calling something else that calls it. So for instance, add calls heapify up. We don't want our end user calling that. The user can call add, the user shouldn't be able to call heapify up. All right, how do we heapify up? First of all, what variables are we going to need as we do this?
A root.
We probably need to figure out what the parent is. I like that. So let's find a parent index. What did we say the parent index is? Now we need to know where the current node is, so. Where is the current index? Get it off by 1 error if we do that. We bumped up size after we did this. Size tells us the number of elements. If we want the index of the last element, it's gonna be size -1. So the parent of current index is going to, in order to get the parent index, we needed to know the current index. So the parent index was what?
Current index -1 divided.
Yeah. Make sure you put those parentheses in there to avoid trying to subtract 1/2. If you subtract 1/2, you're going to get index, or sorry, you're gonna get integer division. Integer division 1/2 is 0. So you get that off by 1 error and you would get an index out of bounds exception. Or you would rather be swapping with the wrong index and wonder what's completely messed up. Those parentheses are crazy important. All right, so now we have our current index and our parent index. Great. Now we're ready to start looking at the current and the parent and seeing if we need to swap them. How would we do this? We could either do it iteratively or we could do it recursively. Just looking at this and thinking about it, which one do you think is going to be easier? Recursion? Any other votes for recursion? Who thinks recursion is going to be easier? Who thinks iteration is going to be easier? For this problem, it's actually almost identically the same. It's going to be about the same amount of code regardless of what you do. So generally, coders have a preference for iteration over recursion, so that's how we're going to implement it. One challenge that I might have for you at the end of this is to look at this and say, how would you implement this recursively if you wanted to do that? So what are our conditions for a while statement. We want to be doing something over and over and over until some condition is false. What is the condition that needs to be true in order to keep swapping? Current index is greater than the parent index? Good idea. So I think we need to stop if we're at the root. So we want to continue while the parent index is greater than or equal to 0. If you go through some process and the parent index ends up being less than 0, then we're at the root and we should stop. There's one other important condition. What is that condition? We need to compare the current to the parent to determine if we want to swap it. Since this is a min heap, we want to continue swapping as long as the current value is less than the parent, because that says that we want to be closer to the root. How do we do that? Since we're not working with integers, we're working with t's. Yeah, we're gonna use the compare to method. So we want to say elements of child index that gets us the value of the child dot compare to elements of the parent index. And should this be greater than, less than or equal to, greater than or equal to 0? What do we know about compare to? Less than, I agree. Strictly less than 0. If that's true, then it is less than. What's up? Sorry? Child index, current index. Yeah, this should be current index, sorry. Thanks. For some reason, I had this in my mind, but this is gonna be the child. And no, it's the current. Okay, so I think this is our while loop. It's a little bit of a long one, a little bit nasty, but I think this is what we want. So as long as this is true, what do we want to do and how do we prepare for the next pass? Swap them? I agree. I'm gonna write a swap method here real quick because I think that we're gonna be doing this a few times in this code and we don't want to rewrite the swap code over and over and over and over. So this is something that, again, we don't want to call from the outside. It's going to return nothing. And it's gonna take, let's call this a child and a parent, since we're never gonna be swapping anything except a child and a parent. And this is gonna be based with the child's location and the parent's location. So we want to, now, if we're gonna do this, we want to save off a temp. It's gonna be of type T. Let's pick, doesn't really matter which one we do here, we'll say elements of child. Then we want to say elements of child gets elements of parent. And elements of parent gets. That's gonna be our swap. So what is our child index for swap in this case? Parent index. And the parent is parent index. So that will do the swap. We want to do the swap because the while was true. How do we prepare for the next pass? Yeah. We want to do this again. But we want to do it for where we swapped the current index to, which is now at the parent index. So the new current index is the old parent index. Or I guess it's the new parent index. Same parent index.
So basically you just swap them and then now you just reassign the names of each one.
Yeah, we're just reassigning the names of the variables to make sure that it's the same logic in the next pass of the loop. There's one more thing we need to do. Yeah. What is the new value of parent index?
You current index minus 1 divided by 2.
Yeah. I already want to factor this out. So maybe we make some private methods that's like get parent. And then we can call get parent on an index and on current index and get back the new index. We'll see if that's necessary.
Can you explain that last line? What is that doing? Is that just making it so you already checked the original parent and then now you're going to the next parent?
Yeah, let's draw this out. I think having a visual for it will make this make a lot more sense. So let's say we have a heap that looks like this. That's 7 things, so this is the equivalent of an array of 7 things, 3, 4, 5, 6, 7. So if we had just inserted right here, and we wanted to heapify up, and let's say that we have the new minimum element, so we want to heapify up all the way to the root. We start with current index pointing here. And parent index pointing here. Where would this be in the associated array? So current index is going to be the very last element. Parent index is going to be index 0, 1, 2, so that points here. So in preparation for the next pass, we're gonna have swapped the values of what was here. But we didn't change current index or parent index. So in preparation for the next pass through the loop, we want current index to be here. We want parent index to be here. So to make this current index and to make this the parent index, we need to set current index. The new value of current index is the old value of parent index. So that's what this line is doing, is saying current, we need to now follow the data. The data moved here, so current index needs to also move here. In preparation for the next pass, we also need to find the location of the new parent index, which we don't currently have a variable for. So to find that, we just subtract 1 divided by 2. And if we're at index 2, we subtract 1 to get 1, divide by 2, integer division, we get 0. So the parent index is now moving from here to here, while current index moves to, where is that? There. So now we're successfully preparing ourselves to do the next swap if this condition is true.
So basically, whenever you do that call for the parent index, it's cutting, you're moving back half the list.
Kind of, we're pretty close. You're finding, you're doing this process. You're moving wherever this happens to be, you're moving up a level. Or up a level, or, yeah. You're moving the current up a level and the parent up a level. The associated new current and new parent. So I think this does it. I think this finishes off heapify up. Heapify up is certainly easier than heapify down. So it's good that we did the easier one first. Does anyone have any questions about the code logic or how the code logic maps to either the tree logic or the array logic. We're implementing it like this, but it represents something that looks like this. All good? It's perfectly okay if the question is, I just don't get it. That's okay. All right, so we have add or insert. We could call this insert. I'm actually gonna call this insert. Since we don't have to follow the exact priority queue, the priority queue calls it add, the interface calls it add, I prefer insert. All right, so we have a swap. I'm gonna keep the next thing above swap. Okay, so we want to now remove. So we want to return what we removed. So we're gonna return something of type T. And remove is going to take nothing, since we don't need any information to be able to remove. Is there any time when we shouldn't be able to remove? We should throw an exception instead. If it's empty, I would completely agree. We should not be able to remove if the heap is empty. So what kind of exception should we throw for that? That would be true if we were passing in something that was, so a legal argument is generally if there's a parameter and we passed in an invalid parameter. Sorry? It'd be out of bounds if we were trying to access something that would be out of bounds. I actually think it's exactly the same exception that we had up here. Where the user is asking us to get into an illegal state. So we can't remove from an empty. So we're going to throw an illegal state exception. If is empty. Say can't remove from an empty heap. Great. To continue with the removal process, what's the next thing that we need to do?
Exception twice.
We're only throwing it once. This is just saying that this method will throw this exception. This is the place that we're throwing it, and this is just the declaration that this method throws this exception. It tells the compiler, if this method throws this exception, that's intended behavior. Great question.
Well, the first element of black.
Yeah, we eventually need to do that. We probably want to store off this value because as soon as we swap it and delete it, we still need access to it because we eventually need to return it. So I'm going to call this variable, I don't know, root. Where is that going to be stored? Index 0. We already know it's not empty, because if it was empty, then we'd throw it, so there's no way we can try to access something that doesn't exist while doing this. Which is why thinking about those exceptions is really important. So we're going to do that, now we've stored it off. Now, once we eventually delete it, our variable root is still keeping track of that value. So let's do the swap. We need a child and a parent. It doesn't really matter what the child and parent are, because usually that's what we're doing. In this case, it's not a child and parent, but we need the two elements to swap. So what are the two elements we're gonna swap? The last one with the first one? What are the associated indices for that? Yeah, size -1 and 0. Since we're getting the indices of that, note that we're already accessing elements of, so we just need to pass in the indices. The indices of what we want to swap. Size is going to be out of bounds, size -1 is the last element. 0 is the first element, so we're swapping the root with the last value. Next, what do we do? We need to delete the old root that is now down in the last position. How do we do that? Since it's of type T, we set it to null, we don't set it to 0 or anything else, we don't know what that data type is. But we know that every object type can be set to null. If we store its, the T is going to be the integer class type, which can take null.
If we're using an array list, if we called the remove
Yeah,
from the array list methods, would that?
that's
no
dangerous,
work?
that's generally dangerous, but the correct thing to do, because it would be moving everything that's after it forward. But if we're deleting the last element and there's nothing after it to move forward. So you get that process for free when you call the array list dot remove. So we want to make sure that the only thing you are ever removing is at index size -1.
So would that change, so say if that did work, would that change the complexity?
In this case, no, because you're always removing the last element. So you're never gonna be moving anything else forwards. You might be doing a check to see if there's anything else to move forwards, but that's gonna be constant time. So it does not change the complexity if you're only ever removing the last element. Great question. What do we do next? I think we want to decrement the size first. Since we just removed something and then we want to call down heapify. There's one last thing we need to do after we return from down heapify. What is that? Yeah, return the root. We know we need to return something of type T. So we know that root was removed, so now we need to return it. So this is going to be the entirety of remove. We just now need to implement down heapify. We are just about out of time, so it probably doesn't make sense to start down heapify. We will start tomorrow's class with implementing down heapify, but we're getting pretty darn close to done with this and being ready to test it. So next class, we're going to finish this off and test it, and then we're going to write a driver that uses heap sort. It's going to use this object that we are making.
Yeah.
I will see you tomorrow for that. Let me know if you have any questions about the assignments. I have office hours starting now.